So every experimental biochemist knows the feeling, right? You've spent months at the bench. You've purified your protein. You've optimized your kinetic assays. You've run the columns. Maybe you've even tried and perhaps failed to obtain a high-resolution crystal, NMR, or cryo-EM structure. So now you're going to turn your efforts to the server room down the hall, or more likely, you'll probably just click on one of the myriad online structural prediction portals that are available on the internets. And on the screen, it looks great. The molecular graphics software loads, the protein breathes, it moves. A small molecule inhibitor just glides perfectly into the pocket. And a neat little text box even appears on the screen. It declares a binding energy of something like minus 9.20 kcals per mole. And so it looks very definitive. It looks beautiful. It looks just like the ultimate answer that reviewer number 2 has been demanding all along. But here's the problem. That digital beauty can be a disastrous and dangerous mirage if you don't actually understand and know how to read the underlying math. So welcome back to Biochemistry Unfolded, from atoms to algorithms. And today I'm going to step out of the wet lab and directly into the high-performance computing cluster. And this episode is a survival field guide written specifically for the bench scientist. So let's count down the 10 biggest misunderstandings and pitfalls that experimentalists fall into when applying computational biophysical data to their work. And to help us navigate this, I'll frame the entire landscape around 2 fundamental mechanical concepts: springs and sand. And so if you can understand how computational biophysics uses springs to build molecules and how it uses sand to track their movements, you may never look at a molecular simulation the same way again. Along the way, we're going to dive into 3 definitive and peer-reviewed papers that you should probably keep on your bench desk the next time you collaborate with computational colleagues or critique an in silico model. So let's all unfold this, shall we? I'm going to kick things off with tip number 1, and that's that docking scores are not experimental binding affinities. And this is arguably the single most common figure padding that we see in modern biochemistry manuscripts. A team docks a library of small molecules against a target receptor. It sees a score of minus 9.5 or minus 10.0 kcal per mole coming out of Autodoc, Vena, Glide, or Mo. And it reports that as a literal value of an experimental KD or IC50, or at least it appears that way. But as we peel back the user interface, we realize that standard molecular docking routines use heuristic scoring functions. They are built for extreme speed. They're designed to triage a library of 100,000 or perhaps millions of compounds over a single weekend. And to achieve that speed, these algorithms cut massive thermodynamic corners. They calculate simple geometric contact points. They count hydrogen bonds. They make rough guesses at concepts that are very important, such as things like desolvation. And so what do they leave out? They largely treat the protein receptor as a rigid block of plastic. They often completely approximate or oversimplify the massive entropic penalty of locking a flexible, freely rotating small molecule into a tight pocket. And they flatten out the incredibly complex behavior of the water networks surrounding that pocket. And so if you want the definitive reality check on this, let's examine the 2014 paper by Guedes and colleagues published in Biophysical Reviews. And so that's entitled Receptor-Ligand Molecular Docking. Guedes systematically breaks down how these scoring functions operate, and they lay bare their mathematical inability to capture true thermodynamic free energy, or delta G. It's imperative to think of a docking score kind of like a rough sorting hat to isolate potential binding poses, as opposed to a quantitative bench value. If you treat it as absolute proof of high affinity, you're probably going to spend thousands of dollars buying or synthesizing compounds that will ultimately turn out to be completely inert in a test tube. Also, if you're interested in studying and reading more information from the papers that I present in this video, every citation is linked in the show notes for the episode, and that's found in the YouTube video description down below. So please go ahead and click on that. So now let's move to tip number 2, and that's to stop treating AlphaFold models as dynamic ensembles. And so tools like AlphaFold, OmegaFold, RosettaFold, ESMFold, they've certainly revolutionized how we design constructs, pick mutation sites, and interpret low-resolution electron density. And they're definitively software engineering triumphs. They're worth every penny that's been spent on their development, certainly. But it's also important to remember that an AlphaFold or an AI structural model is just a snapshot. It predicts a single, highly optimized, thermodynamically baseline backbone conformation. And that was deeply influenced by the historical bias of what was successfully packed into a crystallization lattice and uploaded to the protein data bank. Real proteins in a solution do not live as statues. They exist as dynamic, fluctuating structural ensembles, and they possess open and closed sites. They undergo allosteric transitions when an effector molecule binds just nanometers away from the active site. And so to see how this all manifests, let's check out a key paper by Saldaño and co-workers from 2022 in Bioinformatics, the journal Bioinformatics. And that was entitled The Impact of Protein Conformational Diversity on AlphaFold Predictions. And so in this paper, the authors evaluated how AlphaFold handles proteins known to undergo major structural shifts. What did they conclude? Well, AlphaFold is remarkably good at pinning down a dominant structural state. It frequently struggles to predict alternative functional conformations or capture structural diversity, as illustrated in Figure 4 from the paper. So in Figure 4a, this shows that AlphaFold 2 predictions are more closely match the hollow form or the bound form of ornithine binding protein than the apo or unbound form. Yet in yeast guanylate kinase, in Figure 4b, AlphaFold 2 actually more closely matches the apo form than the hollow form, which is kind of weird. And it does not even closely match either the apo or the hollow forms of nucleoside triphosphate pyrophosphohydrolase in E. coli, and that's in Figure 4c. We've got 3 completely different conclusions here using the same software on 3 different proteins. So relying on a single high-confidence structural model to explain allostery or ligand-induced fit is probably a little bit like trying to master the rules of basketball by staring at a single photograph of Michael Jordan posterizing Alonzo Mourning. Here you end up posterized just like Alonzo did in this photo right here, right? So that brings us to tip number 3. And so understand your scoring functions and your force field. When you transition from simple docking to actual molecular dynamics, or MD, the computer elevates the energy of the system at every single step using an empirical scoring library called a force field. Commonly used force fields in computational biophysics include AMBER, CHARM, and OPLS. Those are probably the three big ones. And so a force field is a mathematical function and parameter set that's used to calculate the potential energy of a system of atoms or molecules. As an experimentalist, you must realize that these force fields are not absolute physical truths, and they're not handed down by nature. They're highly tuned empirical equations that are parameterized using a mix of quantum mechanics and on tiny fragments and macroscopic experimental data, kind of like liquid densities or heat capacities. They do have known biases, and some historical force fields overstabilize alpha helices, others overstabilize random coils. So if your computational data shows a loop that's completely unraveling, you've got to always ask, is this actual real biology, or is it an artifact of the mathematical weights assigned by that specific flavor of force field? Right? So now let's look at how the computer actually visualizes the physical bonds holding a protein together. And that brings us to our first major metaphor, and that's the springs. And so in classical molecular mechanics, quantum mechanics is largely turned off, and that's usually done to save computing power. Electrons are not modeled as clouds using the Schrödinger equation. Instead, atoms are treated as simple spheres with a fixed net charge, and covalent bonds are treated as literal harmonic springs. And so if you recall from your freshman physics course, this is essentially Hooke's law in action. The potential energy of a bond is calculated based on a force constant, and that's the stiffness of the spring. And that's multiplied by the square of how far it stretches from its ideal equilibrium length. That's visualized in the equation shown here. And so this mechanical simplification leads us directly to tip number 4. And this tells us that classical molecular dynamics cannot break or make chemical bonds. And so I once worked with a graduate student that spent weeks running a massive classical MD simulation. And they were trying to capture the exact catalytic step where an active site serine cleaved a peptide bond. They were completely baffled when the substrate just sat in the pocket for a microsecond, vibrating but never actually reacting. And so here's the hard boundary, because classical force fields use fixed atom connectivity. Those harmonic springs cannot break, and new springs cannot form. The spring can stretch if you heat it up, but its mathematical topology is locked forever. If your biochemistry involves covalent inhibitor formation or enzyme catalysis, proton transfers, or transition state stabilization, classical MD is fundamentally blind to it. And so to watch this chemistry happen in real time on a computer, you have to switch to hybrid methods that use quantum mechanics and molecular mechanics, and that's QM-MM methods. In a QM-MM simulation, you draw a boundary line around the active site, and the reacting atoms and electrons are simulated using computationally expensive quantum wave functions, while the rest of the massive protein scaffold is treated with fast classical harmonic springs. And so if you want the definitive text and how this partitioning works, read the classical foundational review by Senn and Thiel from 2009, and that's published in Angewandte Chemie, titled QM/MM Methods for Biomolecular Systems. And this paper details exactly why classical mechanics hits a wall at the electron level and provides the roadmap for how computational biophysics splice quantum reality onto classical scaffolds. And so understanding these springs brings us to tip number 5. Beware of small molecule parameterization pitfalls. Well, the springs and parameters for standard amino acids have been refined over decades by structural biology consortia. Your custom synthesized classical small molecule drug has not. When a computational collaborator inputs a novel ligand, they rely on automated servers such as GAFF or CGenFF to guess the force constants of those springs and the partial charges of those atoms. And the Mo software that we use here in my lab, that actually uses an amber EHT force field to model the small molecules, where it uses amber for most of the rest. So that's where we kind of get Mo EHT force field from by Chemical Computing Group. So if this automated software makes a bad guess on a dihedral angle parameter, for example, if we look at the spring constant of a carbon-carbon bond, and maybe it's not parameterized correctly, the ligand will become artificially rigid or unphysically flexible in the simulation. And so this completely distorts how it docks and binds. And experimentalists must ask their computational teams, how was this ligand parameterized? Did you run quantum mechanical calculations to refine its specific partial charges and torsion profiles? If the answer is no, the ligand is traveling through the simulation with broken springs, and then God only knows what you're going to get, right? The good news is that most modern force fields are pretty well parameterized for the major elements found in biomolecules. And, these elements, I teach my biochemistry students that these are the schnapps elements. That's sulfur, carbon, hydrogen, nitrogen, oxygen, and phosphorus. Things get rather interesting when you get into parameterizing bioinorganic molecules with various metals, such as the iron-sulfur complexes in photosynthesis, or the magnesium in chlorophyll, the molybdo enzymes seen in nitrogenase and xanthine oxidase, or even the zinc ion found in carbonic anhydrase. And so therefore, bioinorganic chemistry is a particular area that requires very special attention here. But let's say your springs are perfectly calibrated, and you want to watch your protein undergo a large structural change, such as enzyme opening its lid to let a substrate enter. Now you're going to run head first into a massive computational barrier. And so now it's time to talk about the second metaphor, and that's the sand. And to understand this challenge, we have to look at tip number 6. Acknowledge the sampling and time scale bottleneck. Because your computer uses explicit harmonic springs to model bonds, it has to capture the fastest physical movements in the system. That is the stretching vibration of something like a carbon-hydrogen bond. And that occurs on a time scale of 1 femtosecond. And that's 10 to the minus 15 seconds. So to solve Newton's equations of motion stably, the computer must calculate the forces on every atom every single femtosecond. And so think about the math here. If you want to simulate just 1 microsecond of real-time protein motion, the computer must calculate those forces sequentially 1 billion times. But big biological events such as allosteric transitions, domain movements, or loop closures are fairly rare events. They don't happen every femtosecond. They happen on microsecond, millisecond, or even a second time scale. And why is that? Because the protein spends most of its life trapped in a deep low energy valley, vibrating back and forth, waiting for a rare, stochastically lucky surge of thermal energy to push it over a massive free energy barrier into the next valley, right? So if you run standard 200 nanosecond simulation, your protein is merely shuffling its feet in place. You're looking at local equilibrium noise, and you're completely missing the macro scale functional transition. And so this is where the sand comes to the rescue. That leads us to tip number 7. Master enhanced sampling concepts such as metadynamics and umbrella sampling. And so to overcome this timescale trap, computational biophysicists use enhanced sampling algorithms. Imagine your protein is trapped in a deep energy valley, a local conformation, and you want it to climb over a mountain pass to see where it goes. And so in an algorithm called metadynamics, the computer tracks the shape of the protein along a specific coordinate pathway called a collective variable. Periodically, at set time intervals, the algorithm drops a tiny repulsive Gaussian energy potential at the protein's current location. Metaphorically, this is kind of like pouring a bucket of virtual sand into the valley right where the protein is sitting. So over the course of the simulation, as more and more sand is deposited, the local energy well fills up. The valley floor rises. Eventually, the valley is completely filled with sand, flattening out the landscape. Deprived of its local minimum, the protein is forced to climb over the mountain pass and drop down into the next adjacent energy valley. Once the simulation concludes, the researchers can invert the total amount of sand that they poured into the wells to calculate a beautiful, mathematically precise map of the true underlying free energy surface. Alternatively, they can use something called umbrella sampling, which works kind of like a series of virtual guide wires. Instead of filling the valley with sand, they drop a succession of harmonic spring restraints along the path, pinning the protein to specific windows along the mountain pass, so it's forced to explore high-energy transition states that it would normally avoid. As a bench scientist, when a collaborator shows you a pathway for an active site loop opening, you should immediately look to see if they use those enhanced sampling techniques. If they just ran standard unbiased MD and claimed that they saw a rare millisecond transition occur in a 100 nanosecond run, you should be highly skeptical. They likely just saw a chaotic, unrepresentative fluke, when in fact they combed the deserts and didn't find squat. And that brings us to tip number 8. That's that explicit solvation and entropic complexity cannot be ignored. And water is not just a passive uniform background with a dielectric constant of 78. In the active site of an enzyme, water molecules act as highly structured structural bridges, network stabilizers, and thermodynamic drivers. The driving force behind many ligand-binding events isn't just the enthalpy of the drug hitting the protein. It's the massive gain in entropy when ordered. highly constrained water molecules are kicked out of a hydrophobic pocket and freed into the bulk solution. If a computational model tries to save time by deleting explicit water molecules, replacing them with a generalized implicit solvent equation, it's going to systematically mischaracterize the thermodynamics of the interface. And so one must always ask, are the waters explicit, or are we accounting for the entropic cost of desolvation? And so tip number 9, that involves running a single trajectory, is the computational equivalent of an n=1 bench assay. And molecular dynamics simulations are deterministic but inherently chaotic systems. Infinitesimal changes in the initial random velocities assigned to the atoms at the start of a run can cause identical starting structures to diverge down entirely different, distinct conformational pathways over time. If you see a paper where the authors ran one single continuous 500 nanosecond simulation, pulled out a single frame, and built an entire biological mechanism around it, they've probably committed a cardinal statistical sin. Well, they did, definitely. That's the exact equivalent of running a Western blot once, seeing a faint band, and throwing away the gel, writing a paper. To see this argued with devastating clarity, let's read a key paper by Knapp, Ospina, and Dean from 2018 in the journal Chemical Information and Modeling. And the title of this paper is Avoiding False Positive Conclusions in Molecular Simulation, the Importance of Replicas. The authors of this paper demonstrate how frequently single MD trajectories generate false positive binding events or misleading conformational states that completely fail to replicate when parallel runs are initiated. In one example illustrated in Figure 1 of this paper, one research group ran molecular dynamics simulations of a highly immunogenic T-cell receptor peptide major histocompatibility complex. We can abbreviate that TCR PMCHC. TCR-PMHC. The group is interested in the number of hydrogen bonds between the two TCR chains, as it's been suggested that the mechanical forces acting on the TCR could be involved in TCR triggering. And so in two separate replicas of the simulation, they find an average number of 12.38 and 19.12 intrachain hydrogen bonds. In the published X-ray structure, the number of hydrogen bonds is counted to 15. So the conclusion from MD analysis is the additional 4 transient hydrogen bonds cause a rigidification within the TCR structure, which is determined to be the cause of the high immunogenicity of the complex. Now, if you increase the number of replicas of the simulation to 100, you can calculate an average number of H bonds at 15.28. And this is almost identical to the value that's observed in the X-ray crystal structure. And this illustrates that studies built on the outcome of one simulation without replicas may lead to false positives in your conclusions. As an experimentalist, you must demand statistical rigor. You need to see independent replicate simulations started with different random velocity seeds. And you must verify that the structural properties have achieved mathematical convergence. If it doesn't replicate in silico, it won't replicate in vitro. And so finally we arrive at tip number 10. Treat computation as a hypothesis generator, not post-hoc proof. This can be seen as a cultural shift in how we handle biochemistry, Too often, computational modeling is treated like dynamic clip art, something pasted into section 4 of a manuscript to give a paper a modern high-tech gloss after all the wet lab work is already finished. The most powerful way to use computational biophysics is as a tight iterative feedback loop. A model should make a specific, highly vulnerable prediction that can be tested at the bench. If the simulation tells you that a specific ligand pose is correct, it should identify a precise, non-obvious residue outside the active site that forms a critical structural contact. Don't just accept the image. Go back to the lab, design a primer, mutate that specific residue to an alanine or a bulky tryptophan, and run the assay. If the binding affinity drops or the kinetics alter exactly as the simulation predicted, you validated the structural ensemble. If it doesn't, your model is wrong. So no matter how you clean the graphics, no matter how clean your graphics look, or how low the root mean square deviation, the RMSD is, you've got a model now, right? So as I wrap up today's episode, let's bring it back to our mechanical foundations. The digital universe of structural biophysics is built on springs, mechanical approximations that give proteins shape, but prevent classical simulations from breaking bonds or handling chemical reactions without quantum mechanical assistance. And to see how these structures move across the vast timescales of living systems, we rely on Senn. Algorithmic tools such as metadynamics that systematically fill up energy values to push our models past their local boundaries. And so when you understand the boundaries of the springs, the utility of the sand, and the necessity of statistical replicates, you stop viewing computational biochemistry as a black box or an absolute truth. You now start viewing it for what it truly is, a remarkably sophisticated, deeply insightful hypothesis generator that tells us exactly where to look, what to mutate, and how to conceptualize the invisible mechanics of the cell. And so thank you for listening to another episode of Biochemistry Unfolded, from atoms to algorithms. So if you're currently trying to bridge the wet lab and dry lab divide in your own research projects, or if you've got a favorite force field artifact story or any type of story that you'd like to share, feel free to put them in the comments below, right down here. And remember, all the publications discussed in this episode are also linked in the show notes in the video description. So please check that out and learn a lot more than what I can cover in a short video such as this. Until next time, keep your springs calibrated, keep your variables sampled, and keep unfolding the science. I'll catch you in the next episode. Thanks for watching.